Hi, welcome to Istagon Engineering. This topic will show on how to model an expansion joint in ETABS software. Although there are several ways on how to model an expansion joint in ETABS, this topic will discuss the simplest way, and I will also show that the result that we expect from our output on ETABS shall be consistent with what we have expected. So in order to simplify the discussion, I have prepared this AutoCAD drawing in order to clearly understand the input data. I have also prepared an ETABS model, but without the expansion joint yet. So in our model, in our AutoCAD drawing, we will be modeling in ETABS the same that we have here in AutoCAD. So in our case, the sample model that I made is consisting of 4 spans in X direction and Y directions. And the expansion joint is located in the middle of the structure, which is along axis C, which is on the left edge of the axis C, left edge of the beam along axis C. The slab is 200 thick and the beam is 450 by 600, and it's all typical. And I made a section which is targeted on section A, and to show and illustrate and explain the expansion joint. So in our section, this is the ledger or the corbel, and this is the bearing pad, which is required usually on the beam because the beam usually has a concentrated load. But when it comes to a slab, usually it's not required to provide bearing pad on the slab because bearing pads on the slab, the slab usually are in linear load while the beam is concentrated load. So here we have the concrete beam and we have the ledger and also the expansion joint. So here we can say that this slab has the freedom to rotate and also to slide in going in horizontally, either going to the right or going to the left. So to further explain this, I made an isometric model with the local axis layout. In this isometric diagram, I have this slab in dotted line or hidden line. So as you can see, the slab is free to rotate along axis 1. So the rotation is along axis 1. So we have to release the slab rotation along axis 1, and also we have to release the axial or the shear along axis 2. But on the vertical, we don't need to release the shear capacity of the slab, because what happened, we have a ledger below it, so it has the capacity to resist the vertical load. So we don't need to release on that axis, that local axis. So also I expect that once we analyze this framing system or the slab, what we would expect, since we have a expansion joint here, we will expect a very small moment, because our fulcrum or the point of support starts from here, and there is a small moment that will develop at the end. And also, but on the other end, where this slab is connected to the beam, you will end up with a little bigger moment, end moment, negative end moment. And in the middle, since this continuous part of the slab, it will create a bigger moment, and this one, this end moment, will be almost exactly the same as the other end moment on the right part. So you will see that this left part and the right part here should be equally the same in magnitude, because this is an end moment and the slab is connected to the beam, so the same as the other this one, which is the slab is connected to the beam. Well, this slab is not connected to the beam because we are making a release on this one. So let's go now to our ETABS model. Our ETABS model is the same exactly as what we have in AutoCAD. So in order to create an expansion joint, we select the slabs and beams along axis C. So and then we say view, show selection only, and then we select these edges of the slab, and then say assign shell uh, edge release. Then, as we have discussed previously, the movement along axis 2 should be released, and the bending moment rotating along axis 1 should also be released. We go back to our AutoCAD. So our movement along axis 2 is released. So we have this one, axis 2, and rotation along axis 1 is also released. So we have rotation along axis 1. So then say apply. Okay. And in addition to that, also the beam should be released in major moment, and the axial capacity at the end. So assign frame release partial fixity. So the axial load on the end should be released, because usually the end is on the right, because usually when I draw the beam, I start from the left going to the right. So the end should be expected that this was the end, and the left end should be the start. So the major moment M33 also should be released. Then apply. Now we say view, show all. Now we expect that the left part in between C as the boundary, the left part of C should be totally isolated from the right part of the frame of the structure. Now let's view display show load. Let me see if there is already load here. Apply. Okay, I already put a load which is 5 kilopascal only. This is just only to show and justify that what we are expecting result should be consistent with our AutoCAD drawing. Now in order to get the result, we have to design the slabs, and in order to design the slab, we have to define the strips. So we go add strips. In this case, we have to include middle strips, because we want to show the one on the between the columns, the strips between the columns. This is called middle strips, and this is A and this is X. So apply. Also B, Y and B, apply, then close. Then also again because we have to adjust it, we select again the strips A and B, and we say edit strips, how to widen the strips, apply. And if you notice it, the strips now So strip width exactly as upper what we expected. So this is the middle strip, column strip, column strip, middle strip, column strip. So the same in x and both x and y direction. So now we can run the our model. We save it first, then we run the model. Now let's see the moment or design this lab first. So we select the stories that we want to design. Okay, we select this one, story 1, which is we have only one floor for simplicity, and then start design. Now this is the result. In our previous drawing, our moment diagram is in the middle strip, so we take the same middle strip. So we have column here and we have column, so we take the middle strips and we take this one. So if you noticed, and even if we select it isolated, if you notice that the moment here is very small compared to the other end, which is bigger. The other end here and the other end here is almost the same. So the output that we were expecting is exactly the same as the ETABS output. So therefore, since our expectation is consistent with our ETABS result, so our expansion joint is working. Now let's see if the actual release is working also. So in order to show that, we can see the shear on the beam, or otherwise we can simulate the live load. Okay, and we can make a 3D. We can animate it. So animate. So if you notice it, there is a total separation between there are total separation between a part which is on the left and the right. So if you look at in the plan also and animate it, there is a total separation. So therefore, our expansion joint is working using this method of modeling in ETABS. Thank you.